Uh, Good morning, everyone. So, what day is it today? 오늘 무슨 날이죠? 오. Okay, okay. So, today is so okay. So I think you are nerd. Okay. nerd가 뭐 한국어로는 약간 덕후 그렇게 할 수 있는데. Okay. So today is Pi Day. So actually, the Pi Day is not famous in Korea. So you know. So So I generated this image from Copilot. So it means that the AI generated this image. So today is Pi Day. And what is pi? Pi is so you know the pi is not, it's a real number, but we cannot represent pi with our number system, right? So it is because the pi, so after this point dot, then there are infinite numbers, okay? So actually it's very long, and then it means that we cannot represent the pi with our number system, okay? But if it's real number, right? So pi day, so we just use the first, normally we first use the first two digits after the point that. So we just call the pi is 3.14. So this kind of discipline, right? So you know, so I explained about some digital design concept, and then we restrict some representation. So actually the analog signal, so we cannot represent the analog signal in our number system, right? So for example, pi, the pi has it's a real number, that means it's real, but we cannot represent with our decimal number system. So we restrict some digit. So that is the kind of discipline. So digital discipline. So we just restrict some representations using only two numbers. Okay. It's not fun, right? Okay. So actually, the today is it's a famous. Actually, today is known as White Day in Korea. So it's day. It is known as some day for couples, but it's not a day for couples. Today is a day for nerds. Okay. It's not fun. Okay. So what did we learn in the previous class? 영어로 이렇게 하는 거 힘듭니다. So we learned about the number systems, actually binary number system, right? So why do we use binary number system in digital system? So it is because, so as I mentioned, each digit of digital data or digital number, so each digit only includes two numbers, 0 and 1. So, and then it's actually the same to the binary number system. In the binary number system, each digit can have only two kinds of numbers, 0 and 1. That's why we use binary number systems for digital data or digital numbers, okay? Instead of a decimal number system, because it's not good for the digital system, right? And then we learned about some it's a kind of terminology. So we learned about the bit. So actually these are very important terminology in the digital systems. So actually in the computer systems, right? We frequently use a terminology bit in the computer system or byte. So byte is a basic basic data unit that represent the size of data in the computer system. So we frequently use the byte. And then, so I also mentioned that the byte is the actually we use the byte address. So which means that the address number 1 represents the size of a byte in the memory, right? Okay. So actually, I explained until this slide, but many students ask about the last question. So assuming you have 4 gigabyte main memory. So in this sentence, so 4 gigabyte represent the size of a memory, right? So it means that the size of memory is the 4 gigabytes. So this is the total size of memory, right? So it is equivalent to the 4 multiplied by 2 to the power of 30, 20 is 30, and this is 5. So it's 8. The 1 byte is 8 bits. So this memory can include this amount of bit data. So it means that this memory can include this amount of digital digit, right? And then I asked that how many bits are required to represent the address of this main memory. So actually we did not learn about some memory systems in this course. So I believe you are not familiar with the memory systems. So so actually the address is similar to the index. So what is the index? What is the index? It's so we can use analogy like this. So this is a condo, and then it's called a condo in USA, United States, but it's called as an apartment in Korea. It's apart. So it's a condo. So actually there are many housing units in the condo, right? So there are many houses in the apartment, right? So actually we can distinguish different housing units with the house number, right? Like this is the house number 0 because we are the people, so the number starts from 0, right? So you are a computer person. So actually in the computer system, the index one number starts from 0, not 1. Okay, so we can say that this unit number is 0, and then this unit number is 1, and this unit number is 2. So these numbers are indexes for mapping the housing unit in a condo or apartment, right? So which means that if we just mention housing number 0, so it means that 0 means the this apartment unit. Okay, so this question is asking that in order to represent this index of this memory system, then how many bits are required. So it asks about the range of addresses, the range of index numbers. So and then we use the byte address. So it means that the address 1 is mapped to the 1 byte of data. So think about this apartment or condo. So actually each housing unit has its own size, like for example, 100 square meter. And then we can say that, the total area of this, total size of this condo is there are 4 units from 0 to 3. It's 400 square meter, right? That is the total size of this house, this housing, this condo, right? So 4 gigabyte, that is the total size of main memory. So it represents the total size of this memory unit. And then memory unit has many byte data, right? And then we use address to represent, to specify a certain byte data, right? So in this memory, actually, this memory can include the 4 multiplied by 2 to the power of 30 byte. Okay, so in order to represent this byte data, we require the number from 0 to 4 multiplied by 2 to the power of 30 minus 1, right? Because I said in the computer system, the numbers start from 0, right? So we require this amount of numbers, right? And then in order to represent this range of numbers, then we require how many bits using the binary number? In order to represent this range of numbers, then we require 4 multiplied by 2 to the power of 30, right? So we learned where is this? So n-bit binary number has how many values? 2 to the power of n, and then range is 0 to 2 to the power of n minus 1, right? So using the n-bit binary number. So in this question, in order to represent this range of number, from 0 to 4 multiplied by 2 to the power of 30 minus 1, then we require this amount of bits, this amount of digits in binary numbers, right? So that's why we require this amount of, sorry. So in order to represent this number, so it is the 2 to the power of 32 minus 1, right? So we require this amount of bit, n equal 32, right? Okay. Because using the n-bit binary number, we can represent from 0 to 2 to the power of n minus 1. And then in this question, we need to represent the number 0 to 2 to the power of 32 minus 1, right? Because it's 4 multiplied by 2 to the power of 30, okay? 2 to the power of 32 minus 1. So we require 32 bit for this address of main memory. Okay? Understand? Okay, so I hope everyone can understand. Okay, so actually, so in the previous class, so we learned about some binary number system and the hexadecimal numbers, and then the only difference is the base. So in the decimal number system, we use a base of 10, and then in the binary number system, we use the base of 2, and the hexadecimal, we use the base of 16. Okay, and then why do we use the hexadecimal number system? So it is because if we just use the binary numbers, then the length of the number can be very long. So the 4-bit of a binary number can be compressed into the one digit. So 1 digit of a hexadecimal number. That's why we frequently use a hexadecimal number in our computer systems. So, and then in the hexadecimal number, so we frequently add 0x. So if you are familiar with the C, then you can find that if we just use the represent the variable like the 0x FF, then it represents the hexadecimal number. Okay. Okay. So now let's discuss about the arithmetic of a binary number system. So I don't think this is difficult. Okay. So how can we add two numbers in our real world? So we just learning about some elementary school math. Okay. So how can we add two numbers? So firstly, we can start from the last digit, the least significant digit. So this is the rightmost digit of the number, right? You start from this number, 4 plus a equal 12. So then we just add the one digit numbers, but the result has two digits, right? But actually we just focus on this digit, okay? So because the result has two digits, actually this number 1, actually 10, it's 1, need to be moved to the next digit, right? And then this is called a carry. It's a carry. Okay. So if we just perform addition for one digit, then we can generate the result for a certain digit, and then a carry can be generated. Right? So the carry is also added to the next digit, like 1 plus 3 plus 6, it becomes 10. And then also carry is generated like this. So why am I explaining this? So, I think everyone knows this about this, right? So why am I explaining? So it's the same. It's the same to the binary number system, right? So these are two binary numbers, and then we can start from the LSB, okay? Least significant bit. And then what is 1 plus 1? 1 plus 1 equal, in the binary number system, 1 plus 1 equal 2, but there's no number 2 in the binary number system. That is 1, 0, right? So the result is actually 0 for this digit, and then carry is generated, and then carry is also added to the next digit numbers. Okay, so 1 plus 1 plus 1 is 1 because it's 3. So the result is 1, and then also carry is generated, and then we can perform addition. So actually the same because the numbers are the same, even though we use the decimal numbers or binary numbers. Actually, number systems are the same. So and then the arithmetic of the number systems is also the same. Okay, we can apply the same principles. Okay, then so why do I need to explain this? So this system just handles binary data or binary numbers. So which means that these systems also perform arithmetic operations such as the addition, subtraction, multiplication, or division. So those are the arithmetic operations. And then I said that the arithmetic operations of the systems is actually the same. So we can apply the same principle because the distance system also handle the same numbers, but the number system is different. The distance system just handle binary numbers, but the baseline principle is the same, and then based on these arithmetic principles, we can design digital systems, right? So that's why I explained this. Also, the next class or maybe today's class, then we will learn about the basic logic gate, and then actually arithmetic operations. These arithmetic operations in this the system can be implemented using basic gates, and basic gates just handles the binary logic like 1 or 0. So that's why I explained this. So we just for the addition, we just focus on the arithmetic operation of a certain digit, and then if addition is performed, then the result, then this is called the sum, because this is addition, and then sum is generated, but sum is just a result of a certain digit, and then carry is generated. Okay, and then carry is propagated to the next digit, and then it is included in the addition of this next digit. Okay, right. So you can do it by yourself. Okay, and for following 4-bit numbers, so the carry can be generated, and then also the sums are generated. So it's a result, the answer, right? So for this arithmetic operation, it's addition. So 1001 plus 0101, then the result, the final result is the 1110, right? So it's easy, right? But for this example, so 1011 plus 0110, then carry is generated, here, so 1. The carry is not generated, but for this digit, the carry is generated, and then carry is generated for this digit, and then the MSB also generate the carry, and then the final result is 10001, obviously, but we need once the overflow of these arithmetic operations. So what is overflow? So actually, for this addition, we just perform 4-bit plus 4-bit data, and then so we can just understand that bit in the system is a kind of hardware resources. So which means that it's a 4-bit data, then we require hardware resources for this 4-bit data, and then another 4-bit data, because it's a operand and another operand B. For the another 4-bit data, we require hardware resource for this another 4-bit data, and then the result is generated. So result is also generated data. Then we require hardware resources for this result. So when we perform, actually in the computer system is the same. Computer system is also hardware, and then for example in the C has the data type, right? Like the integer data type, and then I mentioned that the integer data, the size of an integer data type is 32 bit, right? And then if we just integer, we declare some C variables like the integer A comma B comma C, and then C equal A plus B, then it means that C is the 32-bit data, A is the 32-bit data, and then B is the 32-bit data, right? So in the hardware, so 32-bit, a certain data is performed for arithmetic operations, and we assume that the result has also the same size of bits. So you assume that also is the 32-bit data. So in this example, we just added 4-bit data, 4-bit operands, right? Then we assume that the result is also 4-bit, right? So it's the same. In the C, 32-bit data plus 32-bit data is equal to the 32-bit data in the C. Not Python. Python does not have any data type, the default size of data type. It's the same because the C is very tightly connected to the hardware system. Okay. In the hardware, 4-bit data plus 4-bit data, we expect that the result is also 4-bit data. And what's the problem? Problem is that, in this example, the result needs to have 5 bits. Okay, but hardware can have hardware name. So we can just increase the some bits if required, but for conventionally 4-bit plus 4-bit, we expect 4-bit plus 4-bit is 4-bit. So the result, actually the hardware may store only 4-bit of this final result. Then what is the result? The result should be 10001, but because of lack of hardware resources, then the final result can be 0001. What's the problem? The problem is that the final result is incorrect, right? And then it's very critical actually. If our system or our computer systems generate incorrect results, then no one will use our systems, right? Because our system can generate the incorrect result, and then no one wants incorrect result, right? So, and then this is called overflow. Okay, so overflow means that. So you need to understand that digital systems operate on a fixed number of bits. It's the same to the C. If we just declare a data type in C, this data type in C has the fixed number of bits. Okay, the 32-bit, 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 and then it's the same to the hardware. The Python. So just ignore the Python. Python is kind of more higher level language. Digital system, because this is hardware, digital system operate on a fixed number of bits. So like the 4-bit plus 4-bit is 4-bit. But sometimes because of the overflow, because of the carry generated by MSB, the most significant bit, then the digital system may generate incorrect result. Okay, and then this is called overflow, an overflow. Okay, it's called overflow. Okay, so when result is too big to fit in the fixed number of bits in the digital system, that is called an overflow. Okay, so and then if overflow happens in a digital system, then the system can generate incorrect result. And it's also same to the computer system or computer CPU, right? Because the computer CPU is also is a hardware, it's a digital system. So computer system also work with a fixed number of bits, okay? And then if overflow happens in the CPU, then the CPU can generate incorrect result. So what is required? Actually, what overflow can happen, right? So if we just handle very large numbers, then overflow can happen. So what should we do? We need to detect. So actually, we cannot avoid this one, the fixed number of bits. This is hardware. Okay, so actually the hardware has fixed and then limited resources. We cannot change the amount of resources in the hardware. So hardware resources are fixed. So you need to understand that hardware resources are fixed. Okay, so we need to detect the overflow, and then if overflow happens in the system, then this should be reported. Okay, so which means that the result can be incorrect. So it should be reported, and then it should be handled by software or operating system. Okay, so actually this is very important concept in the digital system. Okay, so because the overflow may generate incorrect result, and then you need to understand that digital system has limited hardware resources, and we cannot change it. Okay, and because of this limited hardware resources, then overflow may happen. So we need to detect overflow in the digital system, and then this overflow needs to be reported to the software. Okay. So now, understand? So now, let's discuss about the signed number system. So actually, until now, we just discussed about the unsigned number system. So what are unsigned numbers? So unsigned. So it means that there is no sign. So unsigned number includes the zero and positive number, right? So zero and positive 1, 2, 3, 4, 5, blah blah blah. But we frequently use signed numbers, right? So signed numbers, the signed number also includes the negative number. So signed number includes the negative numbers, zero and positive numbers. Okay, so which means that we need to represent the sign of a number in order to handle signed numbers. Okay, negative numbers. Now negative numbers are required in our real life, right? Then how can we represent the negative numbers in the binary number system? Actually, think about the sign of the normal numbers, the integer numbers. So how can you represent the sign of an integer number? Integer number is 정수입니다, 정수. Okay, integer number. So a positive or zero, we just can add plus sign, and then for a negative number, we can just add minus sign. But so actually, the sign has only two kinds of it's not number, but so there are only two kinds of signs. Okay, like the plus sign and minus sign. So there are only two kinds of data. So which means that actually we can easily represent the sign of numbers using binary data, right? So for example, we can say that plus sign is 0 and minus sign is 1. Okay, so we can represent this sign of numbers using digital data very easily. Okay, so but we will learn about some two possible concepts of signed binary number system, like the sign and magnitude numbers, and then two complement numbers. Okay, so let's think about the sign and magnitude numbers. So until now, I explained that we learned about some unsigned number. So what is the unsigned number in the binary number system? Actually, each digit is a digit 0, 1, 1, 0. So this is the example. So each digit has the magnitude of power of 2. Right. So this digit, the last digit, has the power of 2 to the power of 0. And then this digit has the size of 2 to the power of 1. And then this MSB has the size of 2 to the power of 3, right? So we just learned that in the binary number system, each digit has the size of a power of 2, and then we can just add up these numbers, right? Like the 0 multiplied by 2 to the power of 3 plus 1 multiplied by 2 to the power of 2 plus blah blah blah. Then we can represent the size, the magnitude of this binary number, because and then it's obvious because this is the unsigned number. Unsigned number only has 0 and positive number. Then how can we represent the negative number? So I mentioned that actually in the positive and negative numbers, so there are only two kinds of numbers: positive numbers and then negative number, and 0 actually. So we can just represent the plus and minus using digital, the binary number easily. So which means that we can just define the sign if for a positive number, we can just use the sign bit 0. And then for the negative number, then we can just define the sign bit is 1. So this is sign and magnitude number system. So sign and magnitude number system means that actually, so this is the 4 digit. Actually, the MSB represent the sign bit. Represent the sign bit. So if the sign bit is 0, then it represents it's positive. And then if the sign bit is 1, then it represents the negative number. Okay? And then the remaining bits represent the magnitude of a number. Okay, this is sign and magnitude number system. So this is the example. So plus 6. So magnitude is the 6. So which means that this is equivalent to 110, but it's plus. So the sign bit is 0, and then the magnitude is 110. And then minus 6. So magnitude is the same, but the sign bit is just minus. So we can just add 1. So this is the sign and magnitude number system. And then actually, so this is similar to our real number system, right? Actually, so like the plus 6 and minus 6. So this number represents the magnitude in the real number system, and we just add the sign, right? So I believe you can easily understand the sign and magnitude number system, because this system is actually the same to our normal number system. But what's the problem? So actually, in the computer systems, we do not use sign and magnitude number system. It is because actually, in the real world, the sign bit is different from the numbers, right? It represents just sign. But in the digital system, sign bit is also represented using a number, a binary number, right? Like 1 and 0. So actually, even though this is the plus 6 and then it's minus 6. This is the minus 6 and then this is the plus 6. But in the computer system, minus is 1 and plus is just 0. It's the same to the number. It's a binary number. So it means that if we just perform addition, like this one, then the system or the hardware cannot distinguish, this is the sign or this is magnitude. Okay, so we can just apply the same addition to the sign and magnitude number system. Then what's the result? The result is 1 0 1 0 0. The correct result should be 0 0 0 0. But actually, if we just perform addition for the sign and magnitude number, the result is 1 0 1 0 0. That's wrong. Right. So this is the problem of the sign and magnitude number system. And then also another problem is that there are two representations of 0. Right? So actually, in the real world, plus 0 is equal to minus 0. Right, obviously, right? And then it's the same to the sign and magnitude number system. So actually, 1 0 0 0 is equal to 0 0 0 0. So there are two representations of 0. So if there are two representations for the same number, actually it may be confusing in the system. Okay, so this is the problem. So actually in the computer system we use the 2's complement numbers. Okay, so 2's complement numbers have the problems of the sign and magnitude numbers. So it means that addition works and then a single representation for 0. Okay, then let's see what is 2's complement number. So actually you can think that we can easily understand about the sign and magnitude numbers. It is because the sign and magnitude system is same to our real numbers, the system of our real numbers. But in the computer system, because of these issues, like addition doesn't work, and then two representations of 0, because of these issues, we use 2's complement number. So you need to understand the 2's complement numbers, right? So then, what is 2's complement numbers? So 1 1 1 0. Actually, in the unsigned number system, so I explained that each digit has the magnitude, so size, right? So this LSB is the size of 2 to the power of 0, and then this is the 2 to the power of 1, this is the 2 to the power of 2, this is the 2 to the power of 3. So each digit has its own size in the unsigned number system. But in the 2's complement number system, like the sign and magnitude, we use the we use the MSB of a number as the sign. Okay, so if the MSB is 1, then 1, then is the minus sign. And then if the MSB is 0, then it's the plus sign. Okay, so it's the same to the sign and magnitude. So we can just check the MSB, the most significant bit of the number, for checking the plus and minus sign of the number. Oh, it's the same, right? But if we just use the 2's complement numbers, then the size of this MSB becomes the minus. Okay? Do you understand? So on the unsigned number, the size of the MSB is the 2 to the power of 3, right? But in the 2's complement number system, the size of this MSB becomes the minus 2 to the power of 3. That is different. Okay? Then, how can you represent the plus 6? Okay, it's the same, actually, right? So it's a plus, so sign bit is 0. Okay, and then because this is 0, then we can say that this we can just define the magnitude of this number like the 110, right? But how about the minus 6? Which means that MSB must be 1 because this is the sign bit, and then actually this represents the minus 8, right? I mentioned that in the 2's complement numbers, the MSB is equivalent to the minus magnitude, minus size. Okay, so it should be minus 8. Then the remaining bits need to be 2, right? Because minus 8 plus 2 equal minus 6. Do you understand? Because in the 2's complement number system, the MSB has the size, minus size. Okay, so in order to make the minus 6, actually, we use the 1 for the MSB, and then this is minus 8 in this example. So the remaining bits need to represent 2. And what is 2? 1, 0, 1. So in the 2's complement number system, it should be 0, 1, 0. Okay, so it's different. It's different from the sign and magnitude number system, right? So it's different. So okay, so you may think that it's not easy. It's somewhat tricky. So it is because this complement number system is different from our real number system. But if the 2's complement number system is applied to the hardware, it is the system, then we can easily, without these issues, we can use the number system without these issues. Okay, okay. So, where is the example? Okay, so let's see the example. let's see the okay, minus 6 plus 6 in the 2's complement number system. Okay, what is the minus 6? This is the 1010 as we calculated, and then 6 is the 0110. So let's perform addition. 1010 plus 0110. So what is the result? It's 0. It's 0 and carriage generated. It's 0 carriage generated. 0 carriage generated. 1. Okay, 1000. But we assume that 4-bit plus 4-bit equal 4-bit. So we just remove this 1 because the result is a 4-bit. Result should be 4-bit. So it's 000. So we can observe that in the 2's complement number system, if we just apply addition for the negative number and positive numbers, then we can generate correct answers. So then what is 0? 0 is 0000, right? In the 2's complement number. What is this number? 1000. This is minus 8 in the 2's complement numbers, because I mentioned that this is the minus 2 to the power of 3. Okay, so 0000 equals 0, and then 1000 is a minus 8 in the 2's complement numbers. Okay, so in the 2's complement number system, the most positive 4-bit number is 0, 1, 1, 1. So this is the largest number, right? The 2's 4-bit 2's complement numbers. Okay, because it's minus, but it's 0, and then it's a plus, plus, plus. Okay, this is the largest number. It's 7, right? Then what's the most negative number? So it's the smallest number. All positive digits are zeros, and then MSB, this is the negative size, so it should be 1. So this is the minus 8. Okay, so this is the smallest number that can be represented using 4-bit 2's complement number. So this is the range of n-bit 2's complement number. Okay, it's minus 2 to the power of n minus 1 and 2 to the power of n minus 1 minus 1. Okay, because it's a 7 and this is 8. Minus 8. Okay, it's the smallest number and this is the largest number. So do you understand? So you can just memorize. Okay, just memorize. So this is the system. Okay, the system is defined. Okay, so it's just definition, like some basic definition in mathematics. So that means that you can just memorize the definition of this number system. So in the 2's complement number system, MSB represents the sign. The MSB also has negative signs. Okay. Okay. Then you can say that 2's complement number system it's somewhat tricky and then complex, because in the real number system you can just change the sign of a certain number. Okay, right? So we can just, if we just use the sign and magnitude number system, then we can easily understand about the number. Like 0110 it's 6, 1110 it's just minus 6. Okay, well, in the 2's complement number system, then how can we represent the minus 6? MSB should be 1. So this represents the minus 8. Then we need to add 2 in order to make the minus 6. Then 0, 1, 0. But it's a little bit tricky, right? Then how can we reverse the sign? So actually the reversing the sign is frequently also used in the real world, right? We can frequently reverse the sign of numbers, right? So this method is not good because it's a little bit complex. So actually we can use this method. So firstly, invert the bits and add 1. Okay? So what does it mean? So this is the example. So we want to represent the -6. Okay? But we can start from the definition of a two's complement number system, but it's not easy. It's not easily connected to our real number system, right? So we can start from the positive number. What is the positive number for this -6? It's +6, right? So we can easily know that, this is the 0, 1, 1, 0, right? So this is the base 2 system, base 2 number system, right? We can easily convert the +6 to the 0, 1, 1, 0. Then how can you make the -6? Firstly, invert the bit. What is the inversion? 0 becomes the 1, or 1 becomes 0. This is the inversion. So this is called inversion. So if we invert all bits of the 0, 1, 1, 0, then it becomes the 1, 0, 0, 1. Then add 1 plus 1, and then it becomes the 1, 1, 0, and then carry 1 or no carry 0, 1. So it is the 1, 0, 1, 0. So it is equivalent to -6. Okay. So in order to reverse the sign, then we can use this method. So you may think, it is a little bit. So actually, it can be also complex. But if the bit, if there are many bits, in the number, then we can easily apply this method. Then we can just get some inverse. We can inverse the sign of a number. So how about the -6 to the +6? So -6 is the 1, 0, 1, 0. Then we want to change the sign of this number to the +6. So we can apply the same method. So 1, 0, 1, 0. So inverse the bit, it becomes the 0, 1, 0, 1, and then +1, and it becomes the 1, 0, 0, 1. So this is the +6. Okay. So just remember, just memorize. In order to inverse the sign of those complement numbers, firstly, invert the bits and add 1. So you may think that this is also complex, but in the hardware, actually, we will learn about the adder later of this course. But you may think that we can actually easily apply this method to the real hardware. Okay. Well, for this time, just memorize. In order to inverse the sign of a number, firstly, invert all bits, and then add 1. Okay. So this is the example. So actually, this is the example. Okay. I already did. Okay. Then I already did this one. Then what's the decimal value of the two's complement number? So this 1001. So I said that this is the minus size. So this is the minus 8, and then 0, 0. This is 1. So what is this one number? So minus 7. Okay. So in the two's complement number, just to remember that, just to memorize that, the MSB, the size of MSB is the negative. It's a negative number. Okay. Only this part is different from the unsigned number. Okay. Oh, this is an answer. I already did 6 plus minus 6. So it should be 0, right? And what is minus 2 plus 6? 3. What is minus 2? So firstly, we need to get 2, okay? Because actually we cannot get minus 2 directly. It's not easy, okay? What is plus 2? Plus 2 equal 0, 0, 1, 0, right? And then enough to make the minus 2. Then we inverse these bits 1, 1, 0, 1, and then plus 1 is the 0, 1, 1, 1, right? So this is the minus 2. And then plus 3 is the it's 0, 0, 1, 1, right? So we can just add the 1, 1, 1, 0 plus 0, 0, 1, 1. Okay, that was the result. Result 1, 0, 1, 0, 1, 0, 1. But we just remove this one. So result is 0, 0, 0, 1. What is the result? It's plus 1. Correct, right? So you can observe that if we use the two's complement number, and then if we apply the same add operations to the two's complement number, then we can get correct answers. Okay. So result. Okay. So then let's think about the subtraction. So what's the subtraction? So Peggy. So actually the subtraction is the subset of addition, right? Because A minus B is equal to the A plus minus B, right? In the real math, A minus B is equal to the A plus minus B, right? A plus and minus B. So how can we perform subtraction? Okay, actually we can just convert this number to the negative number, right? And then if we perform addition for this negative number, then we can calculate the subtraction. Right, it's obviously right. So actually in the hardware, the subtractor. So we can, so in the later of this course, so we will learn how to implement adder. So that is the hardware for addition. But the subtractor, the hardware for subtraction, subtractor can be implemented using adder, because we can apply this property. A minus B is actually equal to the A plus minus B. So this is the example. 3 minus 5 is actually it's equivalent to 3 plus minus 5. So we just generate the 3 here, and then we just use minus 5 instead, and then perform addition. Then we can get the result. Okay. Actually, subtraction. Suppose for the subtraction, we can just implement subtraction using negative, so reversing the sign and addition. Okay. So this is the summary of the number system. So actually, so it can be confusing. So what it is because actually in the real number system we can use the different sign like the plus and minus for the sign of the number. But in the digital system, actually the sign needs to be represented using a number 0 or 1. So it means that even so, for example, this is the 1110. It's the same 1110, but it can represent the different numbers based on the some it's a signed number system or unsigned or two's complement number system. So even though the data is the same, the 1110, but if data is unsigned number, then it is, what is this number? This number is 14, right? With the unsigned number. But if this number is the sign and magnitude number, but we do not use this sign and magnitude number, this number is -6, right? But if this number is the two's complement number, then this is the -8 plus 6 is -2, right? In the digital in the digital system and then data, so the data can be the same, but based on the type of data, then this data represents the different numbers. So you need to consider this one in the digital system because the sign of the number can be also represented using a digital number 0 and 1. Okay. So that's why I frequently mention C. Actually, if you see the data type of the C, the C also has the different data type for the signed number and unsigned number, right? So in the C, if we just use the int A, so normal int, then this is just a signed integer. It represents the signed integer, and then it's two's complement number. Okay. So in order to represent the unsigned number in C, then we need to declare the variable as the unsigned int. So if we just declare a variable like this, unsigned int A, then it means that this A is the unsigned number, like this one. So which means that this in the C, the size of integer is the 32 bit. Okay, so it means that n equal 32 in this table. So which means that if a variable is declared as the unsigned integer, then this number can have has the range of from 0 to 2 to the power of 32 minus 1. So you can find the range of the unsigned number here. Okay. So actually the C distinguishes signed and unsigned data type. But you can understand that in the real hardware, even though the data is the same, but it can represent the different number. So which means that if we want to use the unsigned number in C or unsigned number in C, then we need to declare a variable using the unsigned integer or unsigned long. But I mentioned that if we just use the normal integer, actually we can add the signed before the integer. But if we just use the normal integer, then it represents this is the signed. Okay. Then integer type has the 32 bits. Then what's the range, the possible number that can be stored in this variable? The range of 2's complement is equivalent to the -2 to the n-1, and then 2 to the power of n-1 minus 1. Okay. And I mentioned that in the C, the size of integer is 32 bits. So which means that n is equal 32. So which means if we just declare this this variable as the normal integer, the signed integer, then it can as the range of 2 to the power of 31 to the 2 to the power of 31 minus 1. Okay. So if we want to use the very large number of this range, then we cannot use the signed integer. Okay. So this is summary. So actually we can represent the signed number with some different. We can use the different representation, but you need to remember that in the real digital hardware, we use the unsigned format. We can use the 2's complement format. Okay, and then also you need to calculate the range of the numbers. They can be represented using unsigned format or 2's complement number format. Okay, so this is the example. Okay. Oh, okay. So I okay. Oh, okay. I will explain about this sign extension in the next class. Okay. Any questions? Thank you for listening. See you in the next class. 감사합니다.